The next type of model I want to look at is a model of what's called logistic growth. And so logistic growth has to do with so something like human population, where what you want to do is you want to figure out what the population is going to look like over time. And of course, exponential growth is a completely unrealistic model, even though that's the one that's used first. And the reason why it's an unrealistic model is that, of course, there's only so many people that can fit on Earth at any given time, right? At a certain point, there's going to be more people than can live on the Earth, even just space-wise. Forget about all the forget about the issues of having to like grow food for everybody. Just think about space-wise. We can't continue to grow exponentially forever. It just doesn't make any sense. So to fix this in a better model, is what's called the logistic model or logistic growth. And the idea here is that you're going to figure out, you're going to identify ahead of time what's kind of a maximum population that's allowable, and we'll call that M. And then this is going to kind of curve and asymptote at M eventually. And so logistic growth, this is actually a pretty terrible drawing. So let's try it one more time. But logistic growth is going to be that model where it's going to start to look exponential, and then at a certain point, it's going to just level off. It's just going to level off at M. Okay, where M is, say, the maximum population that's allowable, or whatever we're measuring. Okay, so it's going to asymptote. And so it turns out that the equation here that we're going to look at for logistic growth is that the rate of change of the population, say just a stick of population, is going to be proportional to the population times M minus P, where M is the maximum allowable population. Okay, and so this is basically going to say that this is proportional to not just the population, but the population times the M minus P is the population that we can still grow by. Okay, and so this actually is a reasonable model. It's much more reasonable than exponential, because when P is small, so think about just what happens when the population is small, then this is basically just going to be M, and then this is going to be something like the rate of change of P will be proportional to some constant times P, right? So you get kind of an exponential growth, at least to start with, when P is small. And then when P is close to M, then what's going to happen there is that if P is close to M, this value is going to be small. And when P actually is equal to M, this might even be a better way to think about it. When P and M are equal, there can't be any more growth, because the derivative is going to be 0, meaning that P is going to be a constant, okay, or nearly a constant. And so when M minus P is small, this really slows the growth and you end up asymptoting at M. And so what I want to do is I want to come up with a formula for logistic growth in this video, and then in the next video we'll do an example of a population where we're modeling it using logistic growth. So let's come up with a formula this time. And so what we're going to do is we're going to separate variables. And so we're going to end up with 1 over P times M minus P dP is equal to K dt. Integrate both sides. The integral of the right side is, of course, just kt plus c. And the integral of the left side, we're going to have to do partial fractions. And so I think in this case, it's worth actually just writing out how to do the partial fractions. If we were to have 1 over P times M minus P, this would be some constant over P plus another constant over M minus P. M, by the way, is a constant. And then we can make this a little bit easier to work with by getting rid of the denominators. And then we can think about what's going to happen when P is 0 or when P is equal to M. And so if P is equal to M, then M minus P will be 0, and we're going to have that 1 is equal to B times M, so that B is 1 over M. M. And if P is equal to 0, then that means that 1 is going to be equal to AM, which means that A is also going to be 1 over M. And so this tells us that this is going to be 1 over M times the integral of 1 over P plus 1 over M minus P. Okay, so that's how That's how this differential equation is going to start. And then finally, we can integrate both sides. Since it's in the video, I'm just going to erase this. We don't really need that anymore. You can pause the video if you want to go back and look at that. Now we're going to integrate both sides. We're going to end up with 1 over m natural log of p plus, let's see, the natural log of the absolute value of m minus p times minus 1. That's all times 1 over m. That's equal to kt plus c. And then the absolute value of m minus p, that'll be positive, actually. So we can drop the absolute values there. And so this will be the natural log of p minus the natural log of m minus p equals m kt plus c. Okay, and then finally we can solve for p by combining the logs on the left, exponentiating both sides. So this tells us, let's see, that the natural log of p over m minus p is equal to mkt plus c, so that p over m minus p is equal to e to the mkt plus c. And I'm going to do the usual thing all in one step since we're pros, but e to the c is just going to be another constant. So we'll call that c. And then we want to solve for m. And so there's a few different ways to do this. Let's see. So there's a few different ways to do this. How can we do it? So one way is, let's just do it straightforward. We don't need to be tricky. Let's just multiply both sides by m minus p. So p is m minus p times this quantity, c e to the mkt. And then multiply, so we have mc e to the mkt minus pc e to the mkt. And notice, by the way, and this is important, I now have 2 c's. So whatever I change one, I have to change the other just as much. So in fact, at this point, I'm just going to leave the c's alone, keep the p and the m there. And they don't stand for any specific constant, but whatever this constant is, it's just one constant. So if it shows up twice, it's still only just one number. You could change c to be like m times c or something, but then you'd have to divide by m over here. So it gets kind of be a mess. So I'm just going to keep it the way it is. Anyways, let's solve for p. So I'm going to add pc e to the mkt to both sides. So pc e to the mkt, mc e to the mkt. And then finally, we'll divide by everything that we get when we factor out the p. So our population is going to be mc e to the mkt all over 1 plus c e to the mkt. And I actually want to do just one more thing here, just because this will make this a little bit easier to work with. I'm going to divide top and bottom by the exponential term. So we're going to end up with p is mc over, let's see, e to the minus mkt plus c. Okay, and now if we think about what happens when t goes to infinity, the exponential term will decay to 0, and then we end up with mc over c. So we just get m, which is that maximum population. So it's going to be our equilibrium, or our kind of our maximum population, or terminal population, if you want to think about it like we were talking about terminal velocity in the previous videos. So this is the formula that we're going to get for logistic growth.